Hello everyone and welcome to my channel Chemical Engineering Knowledge. In this lecture we will discuss about the two film theory. In the previous lecture we have discussed about the film theory which was proposed by Nernst. It was about one film like the stationary liquid film for the stationary liquid film on the plate surface. Suppose this is a plate, this is a stationary liquid film which is on the plate. This is a plate surface. Plate surface. This is the stationary liquid layer. So if mass is diffusing in this stationary layer, if the concentration is changing in this stationary liquid layer, then the Nernst film theory will be used for this case. Similarly, in the film theory there was a solid stationary layer. So solid, this was the interface, this was the interface region, and there was a stationary liquid layer. This is a stationary liquid layer. The thickness of the stationary liquid layer was sigma. This was the thickness. There was a bulk concentration in the stationary liquid layer was decreases, and if the component A was reached to the bulk region. So this was, and the concentration of this place was CAI, the interface. This was interfacial region. This was solid, this was liquid. Now in this case we will discuss the two film theory. The two film theory is a modification of Nernst film theory. So in the two film theory, was first proposed by Whitman. So it is a modified form of the Nernst film theory. In the two film theory there is interface. On one side of the interface there is a stationary liquid region, and on the other side of the interface there is a stationary gas layer. This is the interface. This layer is the stationary liquid layer. The thickness of the stationary liquid layer is, suppose it is L2. This is the bulk. On the right side of the stationary liquid layer there is a bulk region of liquid. This is this. On the left hand side of interface there is a stationary gas layer. The thickness of the stationary gas layer is L1. Stationary gas layer. This is the stationary liquid layer. This is the stationary gas layer. The thickness of the stationary gas layer is L1. The thickness of the stationary liquid layer is L2. On the left side of the stationary gas layer is a bulk gas. The concentration in the bulk gas is constant. The concentration in the bulk liquid region is also constant, because the bulk gas and the bulk liquid are well mixed regions. So the concentration in the bulk gas and the concentration of component A in the bulk and the concentration of component A in the bulk gas region and the concentration of component A in the bulk liquid region are constant. So suppose component A is diffusing from the bulk gas. Suppose in absorption cases the component A is diffusing from the bulk gas region to the stationary gas liquid region. Then it comes to the interface region, and then from the interface region the component A is diffusing in the stationary liquid layer. At last, from the stationary liquid layer the component A is diffusing in the bulk liquid region. This is the two-film theory. Two-film theory is nothing but in two-film theory there are two resistance to the transport of material. The two resistance are L1 and L2. These two lengths are resistance to the transport of component A. So two-film theory or two resistance theory is nothing but it shows two resistance to the transport of material or component A. So in the two-film theory, the component A, first of all the component A comes to the stationary gas layer region from the bulk of gas. So the bulk of gas, this is the component A. The concentration of component A in the bulk, in the gas bulk region is Ca1, and the concentration everywhere in the bulk gas region is constant because it is Wilmux region. So first of all the component A comes from the bulk gas region to the from the bulk gas region to the stationary gas layer. This is the stationary gas layer. So the component A is transferred from the bulk gas region to the stationary gas layer. In the stationary gas layer, by diffusional process, by Fick's law of molecular diffusion, the component A was transferred to the interface. The component, first of all, the component A comes from the bulk region to the stationary gas layer region. Then, by molecular diffusion, the component A was transferred in the stationary gas region by molecular diffusion. Concentration of component A in this region can be determined by the Fick's law of molecular diffusion. First of all, the component A comes to the stationary gas layer. In the stationary gas layer, the component was transferred to the interface region by molecular diffusion, and the concentration can be determined in this region by Fick's law of molecular diffusion. So in this region, in this stationary gas layer, concentration is decreasing with the passage with the length or L1. So in this region with the L1, the concentration is decreasing with the L1 with the length of stationary gas layer. So and it can be determined by Fick's law of molecular diffusion from the Fick's first law of molecular diffusion. Similarly, when the concentration of component A reaches to the interface, then at the interface the component A is not accumulated nor destroyed, but when the concentration as the component A comes to the interface, at that time the component A is diffusing out to the liquid stationary layer region. So as the component A reaches to the interface, at that time the component A is dissolving in the stationary liquid layer. And so the component A is dissolving in the stationary liquid layer region. And the concentration of A is decreasing in this region. The concentration of A is decreasing with the L2 direction. This is L2, and this concentration can be determined by the Fick's first law of molecular diffusion. Similarly, when the concentration of component A reaches to some concentration, at this position the concentration of A is Ca(I). It is the concentration of A at the interface. When the component A is Coming from bulk region, it passes to the gas stationary layer, and it come to the interface region. In the interface, the concentration of component A is CAI. Then from the interface, the component A was dissolved in the stationary liquid layer, which have length L2. Then from the stationary liquid layer, the component A was dissolved in the bulk liquid region, and in the bulk liquid region, the concentration of component A was constant, which was Ca2. Everywhere in the bulk of liquid, the concentration is constant because this is a well-mixed region. Similarly, this is a well-mixed region. So, turbulency in this region and this region is high. This is well-mixed region. This is also well-mixed region. Concentration in this region is constant, Ca1. The concentration of Ca is constant, which is Ca2 in this region also. So, mathematical form of two film theory is, we will write two film theory in the form of Fick's law. So, this was the interface. There was interface. This is the gas stationary layer. This is the stationary layer of liquid. This is the bulk of liquid. This is the bulk of gas stationary layer, liquid stationary layer, L2, L1. Component A is coming from the stationary, from the bulk of gas, passes to the gas stationary layer, passes through the liquid stationary layer, coming out to the bulk of liquid. Concentration of A is decreasing in this region. Similarly, concentration of A is decreasing in this region. We will use Fick's law in this layer. We will use Fick's law in this region. This is the interface region. The concentration of A in the interface is CAI. Concentration of A is this position CA1. Concentration of A is this position CA2. At this position, there is no accumulation of component A. So, input of component A will be equal to output of component A to the liquid. So, input to the interface is equal to output from the interface. So, input is equal to output at the interface. So, in this region, we will use Fick's law. At this region, we will also use Fick's first law. So, we know Fick's law that Na is equal to, from Fick's law, you know that Na is equal to minus diffusivity of component A in the component B. Change in the concentration of A would be L direction. Suppose this is the L direction. So, we can, so for the stationary gas layer region, for the stationary gas layer region, this is the two film theory because it shows two film. This is the liquid film, this is the gas film. So, a two film can be, this can be one fluid, this can be other fluid, this can be liquid, this can be gas, this can be liquid, this can be also liquid. So, it depends on the fluid. It can be two liquid, it can be two gases, it can be liquid and gas. So, it depends on the procedure. So, in absorption cases, the one film is liquid film and the other film is the gas film. So, component A is absorbing in the liquid and it passes through two resistances or two films, and that is called two film theory. So, the concentration, how the concentration of component A is changes in this stationary gas layer. So, that will be known by Fick's law, which is Na is equal to minus dAg dCA by L1. Because this is the length, this is L1. This region is this is L1 and this is L2. This is L2. So similarly, Fick's law in the stationary gas layer is this. Fick's law in this stationary liquid layer is dAb dCA by L2. This is L2. So, suppose this is equation 1, this is equation 2. So, from equation 1 and 2, we know that now this diffusivity, this is the diffusivity of component A in the component B in the gas region. This is the component diffusivity of component A in the liquid. So these diffusivity are different from each other. So we will use, so from equation 1 and equation 2 we will get some relation which will be given below. So Na is equal to minus DAB L1 dCA. Equation 1, diffusivity of A and B in the liquid region, dCA by thickness on the liquid layer. This is L1 is thickness on the gas, stationary gas layer. So we know that the concentration, change in concentration in this region is Ca1 minus Cai. In this region the change in concentration is Cai minus Ca2. So in this equation the C delta Ca will be equal to Ca1 minus Cai. This is because this is a decrease and this is increased. This is high concentration. Similarly, this is low concentration and this is the high concentration. So, and the concentration is not accumulated in this region. So, delta Ca will be equal to, this is equation 1. So, from equation 1, delta Ca will be equal to minus DAB L1. Delta Ca will be equal to Ca1 minus Cai. Concentration at the interface. Concentration in the bulk of gas minus concentration of A at the interface. From equation 2, this is equation 2. From equation 2, the flux of A is minus DAB, thickness of the liquid layer, stationary layer, delta Ca, which is concentration of A at the interface minus concentration of A in the bulk of liquid. Okay. So from equation, suppose equation 3, equation number 4. So at the interface the flux is constant. At the interface there is no accumulation. So when component A reaches to the interface, it will directly dissolve in the liquid region. So when the at the interface, when the component A reaches to the interface from the gas region, at that time the component A will directly dissolve in the stationary liquid layer and there will be no accumulation of component A at the interface. So at the interface, input is equal to output. This is input. Equation 3 is input to the interface, and equation 4 is output from the interface. So input is equal to output at the interface. So from equation 3 and 4 we will get the following relation. From equation 3 and 4 we will get the following relation. Na is DAB L1 Ca1 Cai Na DAB L2 Cai Ca2. At the interface these two equations are equal because this is input, this is output, input is equal to output. So we create these two equations. So this is equation 3, equation 4. So from equation 3 and 4, equation 3 is equal to equation 4. So we will get, as the left hand side of the two equations are equal, so the right hand side will also equal. So minus DAB L1 Ca1 minus Cai is equal to minus DAB L2 Cai minus Ca2. Let's go with this. Now diffusivity divided by length is nothing but the mass transfer coefficient. It is the mass transfer coefficient. So DAB divided by L1 is the mass transfer coefficient in the gas region. Actually, for simplicity we will denote DAB divided by L will be denoted by K, mass transfer coefficient. So mass transfer coefficient in the gas region will be denoted by K1. So this term will be equal to K1. It is the mass transfer coefficient in the gas region, mass transfer coefficient in the stationary gas layer, and this will be Ca1 minus Ca(I), and this is the dAB, diffusivity of component A in component B divided by the length of the stationary liquid. So this will be the this dAB divided by L2 will be equal to K2. This was equal to K1. Mass transfer coefficient in the gas region, mass transfer coefficient in the liquid region will be given by K2. Mass transfer coefficient in the gas region will be given by K1. So it will be given by K2. Cai minus Ca2. Now suppose this is equation number 5. Rearrange equation 5. We will get the final equation which will give us the mass transfer coefficient and the concentration, which will give us relation about mass transfer coefficient and the concentration gradient in the two stationary layers of liquid and gas. So it will be, so from equation 5 we will get, from equation 5 and 5 will get K1 Ca1 minus Ci is equal to K2, mass transfer coefficient in the liquid region, mass transfer coefficient in the gas region, Cai minus Ca2. So rearrange this equation like K1 divided by K2 is equal to Cai minus Ca2 divided by Ca1 minus Cai. So this gives us that there is inverse relation between K1 and Ca1 minus Cai. This gradient, there is inverse relation between K1 and this gradient, and similarly there is inverse relation between K2 and this Cai minus Ca2. So if we increase K1, this term will be decreased. If we increase K2, this term will be, if we increase K2, then this whole number will be decreased. If we increase K2, the K will be decreased. If we decrease K2, K will be increased, and K2 depend on this number and also on this number. K1 depend on this number and this number also. So this is all about the two film theory. In the coming lecture we will discuss about the penetration theory, surface renewal theory, boundary layer theory. We will give relation between mass transfer coefficient and diffusivity, and how mass transfer coefficient is related to the diffusivity of component A into the component B. So in the coming lecture we will discuss about the other theory of mass transfer. We will also discuss the distillation, skipping, absorption, leaching, and liquid extraction. These all phenomena will be discussed in the coming lecture of mass transfer. So if you are new to the channel, please like and subscribe. Thanks.